if we consider amorphous, those wires are amorphous, we have the main contribution to the anisotropy energy will bring some contribution to magnetic energy. Magnetic contribution depends on both magnetostriction and internal or external stresses. And what is important in amorphous alloys, it is possible to induce anisotropy and to tailor magnetic structure. So, for example, we have interesting composition, cobalt-based, but without applying stress. The loop is rectangular. But if we apply stress, so the loop becomes, we can change the character of the magnetization process. And all this due to the dependence of magnetostriction on stress. So we can apply external stress, we can go from this blue line to green, right? So to be hysteresis becomes almost without large hysteresis. For the same wire, if it is annealed by current, it is possible to induce, you can see here this red curve, it is possible to induce circular anisotropy. And then if the stress is applied, so for example, this blue line with zero stress, we go back to rectangular hysteresis. Also with these wires, it is possible to find compositions with low Curie temperature. Whilst we are going towards, with temperature, towards the Curie point, which is, say for this composition, is just around 61 degrees Celsius, the character of hysteresis preserves. It's still almost rectangular, up to the very close temperatures, like 58 degrees. But if we're talking about harmonic spectrum, it means that these harmonics will decrease because just of the amplitude of the remagnetization changes. The Curie point can be adjusted by annealing. For example, this is the red one, annealing at 350 degrees. So we can decrease the Curie point to adjust particular application, for example, to control hyperthermia treatments. Skip this. So if we then choose a particular behavior of magnetization process, like in here, we go from blue to green, right? So change from rectangular to inclined. And what happens with the harmonic spectrum, with the stress? So the amplitude of harmonics will decrease with applying stress. So that can be already used for sensing applications. For the wire annealed by current, the situation could be different. So that is the blue curve for zero applied stress, and the red one, rectangular, for higher stresses. In this case, what happens with the stress, the amplitude of, for example, here, that is, I think, kind of 11th harmonic. So the amplitude of harmonic increases. Again, that could be easily detected. This is the example of harmonic spectrum for a number of wires with slightly different Curie temperature. So possible to realize almost linear change in the high harmonics amplitude. In here, this is 13th harmonic shown. This kind of behavior of microwires can be used for controlling the temperature For example, here I took the work by Rostislav Varga. Microwire is embedded into rat, and that there was measuring the change, temperature dependence of the switching field. That is for low frequency magnetization and so generation of high harmonics. But the wires possess magnetoimpedance effect, which is related with the skin effect, and that typical at gigahertz change, we can have the impedance change up to 400%, and even more, 600. But important is that all this happens in quite small magnetic fields, in the range of just few erstat. So the sensitivity is really huge, and that was proposed to for application in very low magnetic fields, for example, for the use in magnetic cardiograms. Recently, it was easily realized the sensitivity up to 3 picotesla at quite low frequencies, below 10 hertz, and was proposed for biomedical signal detection. Actually, in Japan, there was this attempt to do this, and they use two in differential arrangement, 2 wires with coils. So the signal was taken from the coil, so called off-diagonal magnetoimpedance, and they managed to construct an array of such sensors, and each sensor would produce MCG signal, and this is for comparison with electrocardiogram signal. But what is interesting to electrocardiogram signals, but this all another application of magnetoimpedance effect. This is for the detection of magnetic beats. So they would, if they magnetize by this field perpendicular to the, for example, wire surface, this field does not, ray field of the view would have a component along the wire, and impedance would change. And this is a result from Cureax group in Iași, Romania. As I mentioned, impedance remains large sensitivity to the magnetic field at gigahertz frequencies. This is example of impedance change. For example, this red curve about 1 gigahertz, so that at the lower fields, almost the same sensitivity, comparable with that of 100 megahertz. Of course, with further increasing frequencies in this particular wire, the sensitivity actually drops, but still quite significant, few percent per step. And also a little bit different behavior of high frequency impedance for wires with almost rectangular loop. So we hear just this one peak, but again, with increasing frequency, we have quite a significant sensitivity of the impedance change. It was proposed to use this for just we'll skip this, for inducing electrical polarization in the wire at gigahertz frequency. So this is the wire just single standing, and it is placed in high frequency electric field. And what happens with the current in the wire, it is it has some kind of distribution along the length with zero at the ends. It means that there is generation of electric polarization due to the accumulation of charges at the end. And this polarization, in fact, it is possible to calculate this more or less exactly. Session parameter would include 1 Hertz. Close frequency already you can see lower and a little bit higher frequency that the drop in this magnitude. Also, that is demonstration that the amplitude of modulation depends on stress. So that was proposed to be used for various remote sensing of possible stresses near various implants, right? So it is possible to introduce this microwire inside implants. And of course, when we have, say, different microwires of different lengths, so they could be designed for sensing, say, stress and temperature. And all this could be placed inside. So it could be checked on a real person because the distance between the antennas is kind of couple of meters. The other application of magnetic microwires could be for producing high gradient magnetic field, because if we have high gradient magnetic field and M is magnetic moment of a particle, so there is a force acting on these magnetic particles. But in order to move, say, very weak magnetic particles, say even when mark the cells with some nanomagnetic particles, so their sensitivity will be quite low. So we need to realize gradients in the range of, say, up to 10 to 5 Tesla per meter. So in this case, magnetic forces will be larger or comparable with other forces like viscosity, adhesion, and some other forces. There are quite considerable research in this direction, and typically micromagnet arrays are produced from permanent magnets using photolithography. At the edge of the magnet, you will have this field distribution. And so was demonstrated, for example, in this square array of micromagnet, how paramagnetic particles will be distributed in the solution around the poles of this magnet. It is possible to use also microwires magnetized along diameter, magnetized along the axis, and actually quite interesting to realize so-called Brownian motors in wires with this circular magnetization, because we can move the circular domains with very low current, and we will have this periodically traveling magnetic potential. And that allows controlling the velocity of paramagnetic particles. In fact, this the wire magnetized along diameter, there is a question, what kind of field do we need for such magnetization? So we checked, and for iron-based wires, it reaches quite a large magnetization in a relatively small field of millitesla, 100 millitesla. When we have a pair of such wires magnetized along the rear, if the length is, for example, a little bit considerably larger than the wire radius, So that would become this, produce this camel-shaped two-dimensional minima. So then we can think of having diamagnetic trap, right? So if you consider these two wires pair and they are magnetized along diameter, so this possible for the parameters that are quite realistic to have this trap between the wires on the height about one radius that could be calculated. And in fact, for this diamagnetic, when we increase by order of magnitude, from 10 to minus 5 to 10 to minus 4 diamagnetic susceptibility, we have slight increase in the height, but it is still around radius. So we cannot trap far away from the wire systems. But the same, similar with this arrays of magnets, because of course this is a dipole field and it drops quite rapidly when you go away from the poles.
Sorry, what is
those wires magnetized along the axis could be used as magnetic tweezers, as was proposed some time ago. So we also considered the wires, and for the wire of radius A, in our case is kind of 10 to 20 microns, the active area that the wire can impose the field, the force, quite a significant magnitude, would be within this range. So when we go from the wire end to say 7A, so that is kind of in the range of 100 microns. So then the wire can impose force on magnetic particles. But then imposing this force, the particle will rapidly move towards the wire ends and it would end at the surface. To redistribute the wires, it is necessary to remagnetize. So that's why typically you need not just a single wire for this operation, but at least 3 wires. Also interesting result on diffusion. So if you have microwires, say magnetized along the diameter, then you would produce quite large area in which the action of magnetic force would enhance the diffusion. And the calculation shows that considering paramagnetic particles, say in the water, we can redistribute quite significantly within characteristic time of just 30 seconds. So to increase concentration almost twice around this. So that shows the increase in concentration. So 2.5 times. All this, if the wires are used within a biological substance, certainly you have to check their biocompatibility. And also wire is in a glass tube, but because it is long, and typically people say that if the object is longer than tens of microns, so you need to check its whether it is not harmful for biological tissues. And so that was...
You have 3 minutes.
I finished almost. So in fact, those wires are quite not harmful for bioenvironment. So this is the conclusion. So first, we consider it microwires that can be used as embedded sensors due to fast magnetization switching and dynamic magnetoelectric effect. And microwires of those dimensions can produce high gradient.
To it and stress dependence of magnet restriction, but probably internal stresses could be important also for this case. Yeah, do you think? I mean, internal stresses related to the fabrication process.
It's true, of course, internal stresses are important, but I mentioned about the change in magnetization loop under the action of external stresses, and that typically, even according to your work, would be a result of the change in magnetization probably.
Okay, we can discuss it. I think there are two factors at least. One, of course, magnet restriction, and second, okay, we can discuss later. Thank you again.